Hello, welcome to Calculus Lecture 3.7a, where we are going to talk about optimization. Basically, we're just using calculus for decision making. All right, so you will need your note printout, and a highlighter could be useful. So going through this, it says the line tangent to the curve of a function emulates the behavior of the curve near the point of tangency. All right, emulates the behavior of the curve near the point of tangency. Okay, let me just draw that and show you what that means. Let's say you have a function, you've got a curve here, and you're interested in making a decision, let's say right along here. So at this point right here, we have a tangent line equation. So where that tangent line is, you can make some decisions about this function as long as it's pretty close to the curve. Let's say from here to here, the tangent line approximates the curve near the point of tangency. So that's what we're talking about. All right, number 2, on an interval, the sign of the derivative of the function indicates whether the function is increasing or decreasing. So that's what we just did with the first derivative test. Okay, so you are absolutely used to doing that. And then values that make the derivative of a function equal to 0. So critical points are candidates for max and min locations. So with section 3.7, we're trying to find minimums and maximums. Maybe we're trying to minimize cost or maximize profit. So really, you've done some of these in your homework. Some of the word problems I've given you, just kind of a foreshadowing of these types of problems to where we're trying to minimize cost or something like that. So I gave you plenty of room to work. We're going to work one problem here on the front and then a problem here on the back. I gave you plenty of room to do it on the note sheet here. I'm going to work them on the whiteboard. So our first one says the profit, go ahead and put it back on here so we can read through it. The profit of a group of storage rental units can be determined by the following equation, where x is in square feet. What value of x maximizes profit, and then what is the maximum profit? And so we have this equation, f of x is 5,000x minus x squared over 50,000. So to find a maximum, you are going to have to take the derivative, do the first derivative test. So we have f of x is equal to 5,000x minus x squared over 50,000. I'm going to rewrite this. I'm going to divide 50,000 into both components of the numerator. So I'm not going to take the derivative yet, but 5,000 over 50,000 would be 1 over 10, right? 5,000 going to 50,000, so that's 1/10 x minus 1 over 50,000 times x squared. Now we can easily take the derivative. That's going to be 1/10 minus 2 over 50,000 times x. Now let's go ahead, let's see, that's 1/10. Let's reduce that to minus 1 over 25,000x. We're going to set that equal to 0 to find a critical point. So we'd have 1/10. Let's move the 1 over 25,000x to the other side, make it positive. All right, so x is going to be 1/10 divided by 1 over 25,000. So that's going to be 1/10 times 25,000 over 1 if we flip and multiply. So we can get rid of that there, and you'd have x is 2,500, and the unit is square feet. Now let's make sure that this is a maximum. Okay, so it could be a minimum. So we've got negative infinity, infinity. Our critical point is 2,500. So a number to the left of 2,500, let's say, is 1. So it'd be 1/10 minus 1 over 25,000. That's positive. So far so good. And then let's put, I don't know, a million. So 1/10 minus 1 over 25,000 times a million. So we're going to end up being negative on that side. So it is indeed a max. So the maximum is 2,500 square feet. So what is the profit? Don't forget to answer the second part of the question. That's going to be f of 2,500. So we're just plugging 2,500 back into the original equation. 5,000 times 2,500 minus 2,500 squared over 50,000. All right, and that is $125, which that is not very much money. So I would probably not do this project. All right. So there you go. We're just finding a max or min based on the function. So not really new work. It's just doing a word problem. So the next problem is a little more interesting and a little more like the homework. It's called the fence problem. So it says a rectangular pen must be built using one of the walls of a barn and 100 feet of fencing. What dimensions will maximize the area of the pen? Well, usually with these types of problems, we just want to draw it out. Okay, so we have, let's draw a picture here. We've got a barn. I'll draw that in green. Okay, here's the ridge of the roof. All right, got a barn there. And then we have built using the barn as one of the sides, we built a rectangular pen. So I'll do that in black. And we need to label the dimensions. Since it's rectangular, I'm just going to call the horizontal X and the two vertical portions of the pen as Y. Okay, and then we've got the barn. So in this particular case, and in most of the homework you're going to be doing in 3.7, you'll end up with two equations and two unknowns. So we know that the pen is made up of 100 feet of fencing. So we don't count the barn side, but the fencing. So we need an equation for that. We need an equation that adds up to 100. So that would be x plus 2y is equal to 100. I hope you remember in pre-cal doing these types of problems. You can get those notes out and take a look at them and find those types of problems in the first semester. So x plus 2y is equal to 100. Now we're trying to maximize the area. So I have to have an equation for area, and we know of a rectangle, it's length times width. So in this case, area is equal to x times y. So what I want to do is make a substitution so that my area will just have a single variable, not two variables. So we can rewrite this equation as x is equal to 100 minus 2y. So see, I just put the 2y over to the other side, made it negative, And now I can substitute that in for x right here. So we have area is equal to 100 minus 2y times y. Okay, let's go ahead and distribute. So I'd have area is 100y minus 2y squared. So this is the equation that I need to maximize. Area, the area equation. Now I only have one unknown. So let's do the first derivative test. Area prime is going to be 100 minus 4y. And to find a maximum, we've got to set that equal to 0. So 100 equals 4y, 25, and that is feet, I believe. Yeah, feet, is equal to y. Okay, now we can make sure, just make sure real quickly that this is a max. Okay, to the left, let's say it's 100 minus 4, that's positive. And then to right, let's say it's 100 minus 400 would be negative. So it is indeed a max. So we can now find x because we have an equation, 100 minus 2 times 25, 100 minus 2y. So that's 100 minus 50. So the x dimension is 50 feet. So our y dimension is 25 feet. Our x dimension is 50 feet. All right, so there you have it. Those two examples should be enough for you to do the homework. The homework consists of only 3 problems. On page 210, number 15, number 16, and number 17, and the answer to number 16, since it's even, I went ahead and gave you the answer here on the page. So you put that here, homework. So on page 210, you're going to do 15, 16, and 17. Let's take a look at those real quick, just in case there are any hints that you need. I haven't looked at these in quite a while myself, so all right, page 210. Excuse my not being open to that page. All right, page 210, number 15. That's kind of like the example that we did, trying to minimize the amount of fencing, but they gave you area, so you'll do 2 equations, an equation for area, an equation for fencing there. Number 16, they've done a nice picture for you here, so you can kind of get that in your head. What dimensions will, so that the enclosed area will be a maximum. So that's not just a singular pin here, but the entire pin. So you'll have 2 equations and 2 unknowns there. And on number 17, part A and part B really aren't calculus. You'll just be finding the volume, and then you will do so remember the surface area, these are cubes or 6-sided. So for surface area, it would be 6 times the area of each face. So you'll have an equation for surface area that adds up to 150. So you could use x's and y's for that. And then you want to maximize the volume. So the volume would be, you'll just have to come up with an equation with, say, x's and y's. But remember, volume is length times width times height on that. So you'll have 2 equations, 2 unknowns, just like we did with the barn example that I did for you. So there you go. Give it a try, and I will talk to you on the solutions video.